Hello.
Yes, sir.
Yeah, Vaishnavi, I am just sharing my screen. Please tell me that are you able to see it correctly or not? Okay.
Yes, sir.
Okay, let me share it.
Okay.
Are you able to see my PPT?
Yes, sir. It's clear.
Okay. Uh, am I also visible to you?
Yes, sir, you are.
Okay, okay. And slides are changing?
Yes, slides are changing.
Okay, okay. Thank you for information. Okay. Good evening, everyone. So today we are in live session 6, week 6 for the NPTEL course Non-Conventional Energy Resources. The course instructor for this course is Professor Pratap Haridos from IIT Madras, and I am his TA, Amit Kumar Sharma. So today we will just revise the week 6 content and we will solve some sample problems on based on the week 6 content. This session is recording is on, so we will provide you the recording link and we will also provide you the, the PPT also, so that will be helpful for you. Okay, let's start with the week 6. So just revise from the week 5, just basic, just 1 or 2 slides, just basic revision. So that will be good for this week also. Like key difference between intrinsic and extrinsic semiconductors, we have covered this. Like intrinsic semiconductor, semiconductor is in its purest form, and in extrinsic semiconductor is in its impure form. Are you able to see the pointer? Hello.
Yes, sir.
Okay, I am underlining. Are you able to see it?
Yes.
Okay, okay, thank you. So intrinsic semiconductor, it has low conductivity. The band gap between the conduction and valence band is quite narrow. Fermi level can be found in the forbidden energy gap. Okay, the temperature alone determines electrical conductivity, and the pure silicon and germanium crystalline forms are examples. So these are the basic for the intrinsic semiconductor, and for extrinsic semiconductor, it is in impure form. It has higher conductivity than intrinsic semiconductor. The energy gap is greater than that of intrinsic semiconductor. The presence of a Fermi level depends on type of extrinsic semiconductor, because uh, we are doping in these materials, so the Fermi level depends on the extrinsic semiconductor, which type of doping is there, amount of doping is there, and all. Electrical conductivity in a pure semiconductor is affected by temperature as well as the quantity of the impurity doping. So in this, the electrical conductivity is based on temperature and impurity doping also. And on the other side, intrinsic only depend on temperature. The doping or like impurities such as like AS, SB, P, IN, BIL, and others are doped with germanium and silicon atoms. So these are some impurities which can be introduced in silicon or germanium. So these type of we have like covered. Like for insulator, basically there are two bands, conduction band and valence band. So there is a particular gap easy. So for the electrons to move from valence band to the conduction band, we need some this potential easy. So solar radiation incident on this material and give the energy to the electron. So the electron will take the energy and go to the conduction band. So these are the band gap for insulator. It's more than 2 electrovolt. For semiconductor, less than 2 electrovolt. And for metals, these are partially filled. And there are two options like overlapping metals. So these were the basics, little basic about the semiconductors. Now forward bias and reverse bias. So as you see in the forward bias, this part is connected with the P part. This is N part. So the P is connected with the positive terminal and the N is connected with the negative terminal. Okay. So from this side, this terminal is pushing the pumping the holes to the P side, and from negative terminal, it pushing the or pumping the electron to the this side. Okay. So after some time, because electrons are just combining here, so after some time, because holes are continuously coming, so they will occupy these locations, like these electrons will occupy the holes. Okay, so after some time, this stable operation will be occur. Okay, so you can see that this is the current exchange region. Okay, so this will be in the forward bias. So you can see here the del E upon del x equals to rho upon E will be negative and then positive, because in this region you can see the more negatives are there and in this positives, and the slope is also, this is slope, so you can see this is negative and this is positive, so slope will be negative up to this point and after it will become positive. For voltage it's minus E, so it will be minus rho E, so this is negative, so this will be positive, so this area will be positive, and this is negative, this is positive increasing slope, this will be negative slope. Okay, in reverse bias, the P side is connected with the negative terminal and the N side is connected with the positive terminal. Okay, okay, so because in this the electrons are pumping from the negative terminal to the P side and also from N side, so here you can see that the more number of electrons will be accumulated here as compared to the forward bias. So now what will happen, because the concentration of electron is more in this area, you can see, so when a new electron will come, this will resist. Okay, so you can see the current region is more, so it will have more resistance. Okay, so forward bias will be more, or you can say the for solar PV semiconductors we use forward bias. This is the IV characteristic, you can see. Is my screen visible? Anyone? Is it okay?
Yes, sir. Screen is visible.
Okay, PPT is also changing. If any issue, please let me know. Okay.
Yes, sir. I'll tell you.
Okay. So this is the IV characteristic. Is very important actually. For forward bias, you can see after certain voltage, the current is also increasing when the voltage is increasing. Okay, as we have already discussed that after certain time, this is charge. The current relation charge is very small. So this is a steady. You can see there is steady increase in current with the voltage in the forward bias. But on the other side, in the reverse bias, you can see when you go left side from the origin, if you're increasing the voltage, there is no current. Current is zero, because you can see the more number of electrons are here and more number of holes are here. So when a new electron or new hole is going, they are having resistance, because they are already plus and more plus are coming. So same ion will have repulsive in nature, so they will have repulsion, so there is no current. After a certain voltage, some breakout will happen, and the current will be very high. But this will not work because that voltage is very high. Okay, so the semiconductor material will fail. So normally we use forward bias. So for forward bias, you can see after certain voltage, there is a linear characteristics of IV curve. For reverse bias, there is no such type of characteristics. You can say you can see in this PN junction. So this is the valence band, and this is the conduction band. This is also valence band and conduction band. So you can see the more important thing is here is to see is that the potential for conduction band is higher, and this is the potential for conduction band. Okay, this is for valence band, and this is for valence band. When the PN junction is formed, you can see the bending is there. Okay, so there is a potential bending is there. So here you can see that the Fermi level. Okay, so the Fermi level for the this P and Fermi level for the N junction try to come in balance. You can see that try to become same, because when these Fermi levels are same, then only the junction will behave correctly. Okay, so you can see that this is in straight line. So the Fermi level for both P and N is equal, but for both sides the potential for conduction are different. For P, it is very high, you can see, and for the N, as compared to this Fermi level, it is low. So initially, you can see here also. So these are the like holes in valence band and the electrons in conduction band. Okay. So when the incoming solar radiation is coming, so they will try to come in a balanced state. Okay, so here you can see that in this near Fermi level, this junction, you can see that these are electrons and these are the holes, and very less potential is required. Okay, otherwise if you only see the P section, so you require huge potential. For N section, you require again huge potential. But if you see the complete PN junction, then you can see the the bending in the electron band is occur, and you can see the Fermi level is similar, and you can see the holes and electrons are just only a little voltage apart. So with the incoming solar radiation, we can get the current, photoelectric current. Okay, this is the PN junction. We have covered the bending in detail in our previous class, so you can refer those classes. Yeah, so for PN junction, you can see more holes will be come in the valence band, and more electrons will come in the conduction band, and the Fermi level is like this. So the junction will form, and as we have already covered, like this forward bias. Okay, this type of current collection region will be established, and we can get the current. Okay. So one point is to be considered is to the we have to consider these important points when we are like studying the PN junction working. Okay. So the first is need to minimize the recombination. So recombination means, like suppose this is the valence, this is the conduction band, and this is the valence band. This is the conduction band, this is the valence band. So one electron is going to the conduction band, but after some time, it's again the hole is creating here, and electron is here. But again, it is coming back to this hole. Okay, so it's recombining. So this recombination we have to minimize. Okay, and the effect of defects, and defect also like hamper the like this Fermi potential. So we need to see the defects: single crystalline, polycrystalline, and amorphous. So these three crystal structures we have already covered in our previous classes. So based on the quality of crystalline, okay, based on the quality of semiconductor, like it's single crystalline, polycrystalline, amorphous. So the efficiency of PN junction, or you can see the efficiency to convert the solar energy into electrical energy, will depend on these the crystalline structure. Okay, because the potential also, the band gap potential will depend on the crystalline structure, and this band gap potential also depend on the defects. If more defects are there, means the potential will be not enough, the potential will be affected, and we will not get the required results. So there is a trade-off between cost and efficiency. So as we have already covered in our last class that we have various methods to make the semiconductor for single crystalline, and single crystalline is very costly actually as compared to polycrystalline and then amorphous. So if you go from these three perspectives, the cost is from single crystalline to amorphous is decreasing. The single crystalline is most costly and the amorphous is least costly, and the efficiency will be increasing because single crystalline will be, you can say, a single crystalline structure. So the p-n junction form will be very defect free and very clear. So the efficiency will be more as compared to the amorphous. So now this is very important, like solar cell is a current source. Okay, and the charge carriers created by sunlight received is photocurrent referred by the IPH. So whenever I am writing, or in the notes IPH is writing, it will be referred to the photocurrent. Without external load, the p-n junction is forward biased internally. So when there is no external load applied, the p-n junction is forward biased. Okay. And the solar current is current source, means it is directly converting the solar energy into the current, and so the current is flowing, and based on the other, like you can see the resistance, based on the load applied, the voltage will be there. So it is directly generating the current. So you can see this is the direction of current. So this will be direction of conventional current. So positive ions will flow in this direction, and electron will flow in opposite direction. Okay, this is diode referred as the solar cell, you can say. So here we can see the pH. pH is the photocurrent, the current due to the solar radiation. So when we apply the load, this is free circuit without any load. Circuit number 1. In circuit number 2, you can see there is a RL. RL is load resistance. So we have applied some load. So suppose this current is flowing from this. Okay. So at this terminal, current is IPH is there. Some current will also go in this. Okay. So some current, suppose I is there, and there is resistance. So some voltage difference will be as these terminals. Okay, we will see it in our further slides. So in second number, you can see the solar cell with load applied. Now in third diagram, there is one RS is introduced. So RS is the contact resistance. So as you know that there is like semiconductor material, there are some contacts also, terminals also. So based on that, they will have some resistance. So we are considering RS, it will connected in the series to the load resistance. So this is contact resistance, RS. And in fourth one, there is also a shunt resistance. This is due to the recombination, okay? Because this will due to the recombination, okay? So this is also, this will be in parallel, okay? We will look at in next our further slides, okay? This is the shunt resistance. So you can see in the one simple solar cell, in 2 there is load resistance, in 3 there is contact resistance and load resistance, and in 4 there is contact resistance, load resistance and shunt resistance. Okay, the shunt resistance is having a major factor in like new solar cells or old solar cells. Okay, we will look it further. So these are the IV characteristics for solar cell. We have also seen like for forward bias, the IV after certain voltage is quite linear, but for reverse bias, you can see there is no current with the increasing voltage, but after certain voltage at this point, there is a very high current. So this is the failure of the material. Okay, so we will work in forward bias. So this is the equation. So this is considered as diode. Okay, diode. This is diode. So the current from this diode will be ID. ID. Okay. Then actually we have seen in figure 4 or figure 3 there are some resistance are there like contact resistance, load resistance and shunt resistance. So based on that you have to find out the current. We are having some photocurrent, okay, the current generated from the solar radiation from the solar cell, but in actual the current will be different because due to resistance there will be some losses. So the ID will be I0 bracket e to the power q Vd upon gamma kt minus 1, where Vd is the diode voltage, K is the Boltzmann constant, Q is the charge, gamma is again a constant, T is the temperature. So this is a relationship. For the derivation, you can refer some semiconductor reference book where you can find the complete derivation. But for the simplification, just consider this equation: ID equals to I naught bracket e to the power q Vd upon gamma kt minus 1. So now in this section we will look about the derivation of open circuit voltage, load voltage, and the diode voltage and all. So here you can see the photoelectric current. Okay, this diode, shunt resistance. This is contact resistance. This is load resistance. Okay, so this current will be IL, that will be go towards the load, and this current will be ID. Okay, So you can say that what will be the load current? It will be IPH minus ID equals to IL, because IPH is going from here and is converting two parts, this one part and this part, ID part and IL part, and we are assuming that recombination current is quite very low. So we are considering the shunt resistance is very high, so no current is flowing from the shunt resistance. So we are assuming that the recombination current is very low. So we can write that IPH minus ID equals to IL. Okay. From our previous slide, we know that ID is equals to I naught bracket e to the power q Vd upon gamma kt minus 1. Now we will find out the value of this Vd. Okay. We will solve this equation for the complete derivation. You can refer the you can refer the week 6 videos by Professor Pratap Haridos sir. Okay, in those videos they have completely derived this equation. Okay, we'll find out the value of Vd, or similarly, like this current, the voltage Vd will be the voltage across this diode will be voltage Vd equals to voltage across this VL, voltage across these terminals VL plus IL RS, because there is some resistance RS, contact resistance is also there. So IL current is flowing, so some voltage drop will be there, so that will be IL into RS, because we know that V equals to IR. So based on this concept, this VRS, you can say VRS will be IL and RS. IL is the current from this resistance and RS is the resistance value. So VD will be VL plus ILRS. Okay. Now you can write this. What will be the voltage drop across this load? So VL, you can write VD minus IL RS, and the value of VD you can find out by solving this equation. Okay, just divide the I naught to ID, then transfer this one to left side and take the logarithmic and divide the further equation. So the value of this VD is this. After solving, you get gamma kt upon q log IPH minus IL upon I naught plus 1. So put this VD value in this equation, you will get VL. So VL will be this. You can say equation B. So VL will be gamma kt upon q log IPH minus IL upon I0 plus 1 minus IL RS. So this will be the load voltage when we are having contact resistance. Okay, and we are having some applied load. Now if we have to find out the open circuit voltage. So what is the meaning of open circuit voltage? Open circuit voltage is a voltage when there is no applied load. So you can say that this RL will be 0, IL will be 0. Okay, because there is no applied load, so there will be no current flowing from that load and there will be no resistance. So to find out the open circuit voltage, put the IL value is equal to 0. Okay, so put the value of IL equal to 0 in the equation B, you will get this equation, gamma kt upon q log IPH upon I naught plus 1, because this will be 0, this is also 0. So this will be the expression for open circuit voltage. You can consider it C. So this C expression is for open circuit voltage. From this C equation, we can have some important parameters. We can say that this VOC is directly proportional to the temperature. Okay, because this gamma is constant, K constant, Q constant. Okay, T. So if you increase the T, VOC will increase. If you decrease the T, VOC will decrease. So VOC is depending on the temperature. Also, we can see that VOC is depending on the this IPH. Okay, and IPH is photocurrent. So open circuit voltage also depending on the photocurrent. Now further, if we have to consider the shunt resistance, okay, then we have to also consider the flow of some shunt current also ISH. So this equation will be further modified because earlier it was IPH minus ID equals to IL only. Okay. Let me clear to you. Yeah. So earlier some IPH current was flowing from here. Okay. Some ID part was going here. Then IL part, and we have considered the recombination current is low, so there was no current from this RSS. But now suppose if the recombination current is not low and there is some recombination is occurring, so there will be recombination resistance also. So some current will flow from this resistance. Okay, that will be ISH. So now this IPH is bifurcating in three parts: ID, ISH, and IL. So we can write IPH equals to IL. IPH equals to, we can write IPH equals to IL plus ID plus ISH. Now suppose if you have to find out the IL value, then just send the ID and ISH to the left hand side. So you will get IL equals to IPH minus ID minus ISH. Now you know the value of ID. Okay. The value of ISH will be VL plus ILRS, because this VL is considering voltage across this. Okay. Voltage across this will be the total voltage across this terminal. Okay, if we have to find out the current from this terminal, then we need to know the voltage from these two terminals, terminal A or terminal B. So we have to know, and these RS and R are in series. So we have to write the voltage will be VL, voltage across this terminal VL, we know it from this equation B. For RS, we know VL equals to ILRS, so it will be VL plus IRS upon RSH, this resistance RSH. So this will be the value of ISH, shunt current. Okay. So the IL will be IPH minus I naught. The value of I naught we have already, the value of ID we already know. Okay. And in this also put the value of this VD, VL plus IL RSH. Okay. Because the terminal, the voltage with it will be same. Okay. So again VL plus ILRS upon gamma KT minus. So this is the equation D. So this is the final equation for the current IL that is flowing through the external circuit when some radiation is striking the semiconductor, okay, or PN junction. So this is the expression. it looks very complicated. Okay, so IL equals to IPH minus I naught bracket e to the power q VL plus IL RS upon gamma KT minus 1 minus again bracket VL upon IL plus RS upon RSH. Now we will look about the trend of V and I for this expression. Let's see. So for actual the IV characteristic will look like this. So based on the value we have the value of current, we have the value of load current, IL we have derived from here. So you can see this expression is in terms of IL and VL, because IPH will be constant like I naught is we know, gamma KTQ, okay, RSH, okay. So IL and VL are varying. So we have to draw the IV characteristics IL and VL. So the characteristic will be like this. You can see that for if you are at 0 0, okay, if the voltage is 0 means you are short circuiting the circuit, so the current you will get, that will be short circuit current, that is referred as ISC. So ISC is the short circuit current. Okay, so at 0 voltage you are getting short circuit current. At 0 current, if you are having 0 current, like no current is flowing through the circuit, okay, it means that you have not connected the load. So when the load is not connected, then there will be, if load is not connected, if load is not connected, then there will be no current flowing through that circuit, because circuit is not complete. So we will get some voltage. That voltage is called open circuit voltage, VOC. VOC. So VOC is open circuit voltage when there is no load, and ISC is a short circuit current at 0 voltage. So the if you can see, if voltage is increasing from 0 to some value towards the VOC, the current is quite similar up to a certain point. Very high current is very high. Okay. So at this point and after a certain voltage, the current start decreasing. Okay. So after certain voltage, the current start decreasing, and we know that power is V into I. Okay. Power in watt, and power is you can, the expression of power is VI. So V is in voltage and I is in ampere. So for any system, our aim is to get high power. So we need the V and I value such that we get maximum power. Okay. So for suppose if we operate in this region, then your I is high, but V is low. If you operate in this region, then again V is low, I is high. So we need to find the optimum location, optimum voltage, where the voltage is high, the current is high, and we get the maximum power. So that will be around at this point. So at this voltage, the current is also high and voltage is also high. So we get the maximum power. So our aim to operate the cell at this particular voltage, so we can get the maximum current. Okay. So we will look about it more in our further slides. That's okay. So yeah. So based on this, we can find out the maximum power point. Okay. So we can find out the maximum power point. Now, if we match the ISC and VOSC, open circuit voltage, short circuit current, we can find out this location A, and based on for maximum power that is practically possible, that will be near about at this point, location B. Okay, so you can see there's a difference between A and B. So this B will be maximum power point and it will be determined. So we are having a fill factor based on this data, because this ISC and VOC will be same, but this way, but this trend between the source current and open circuit voltage can change. It can be like similar this, or you can say like this. Okay, so this point can change for different semiconductors. Okay, so whenever we want to purchase, we try to get the maximum fill factor. Okay, so the fill factor formula is like this: VMPP IMPP upon VOC into ISC. So this is IMPP and this is VMPP. Okay, so IMPP and VMPP. So our aim is to get the fill factor is near 1, because if the fill factor value is 1, then what will happen? This VMP will be equal to VOC and IMP will be equal to ISC at this point. So it is not possible. So fill factor value should be near 1. So that value will indicate the efficiency of that solar panel. Okay, that PN junction. Okay, so the formula of fill factor is very important, and it's a very important consideration to find out the best solar panel. Okay, because open circuit voltage can same. So whenever you go to the market, suppose there are number of panels available, and they all saying that we are getting like 18 volt of OCV. Okay, but there is a huge variation in the prices. Okay, so OCV is not an important criteria to decide the solar panel. Okay, so the important criteria should be this fill factor, because this fill factor will tell us that how efficiently the solar panel will generate the power. Okay, so whenever you go to the market, try to ask the vendor that what is the fill factor for this particular solar panel. Okay, because if suppose there are 3 solar panel with same 18 volt OCV, but fill factor can be 0.7, 0.6 and zero point 0.5. Okay, so maybe the 0.51 will be have less cost as compared to 0.7, because this is have high fill factor. Okay, so this curve will be like, you can say this curve is for A, this is for B, and this is for C. Okay, this is A, this is B, this is C. So if you purchase the panel based on only OCV, then you will go like for this panel, but for this panel you can see the IV characteristics, you will not get the so much of power. Okay, so you should get the panel A, which is near to the fill factor value 1. Okay, so yeah, in this diagram we can see there are 3 panels. Okay, 3 diagrams have shown. So this one, 1, 2 and 3. So this is the highest fill factor value as compared to 2, as compared to 3. Now this photocurrent is also depend on incident sunlight. Okay, and the VOC is depend on temperature and this photocurrent. Okay, so if the variation from this IV characteristic, you can see that there is high variation in the current. Okay, but on the other side there is very less variation in voltage, OCV. Okay, so again this data also show that the OCV is not an important parameter to select the solar panel. Okay, again the important parameter will be fill factor, because you can see the fill factor will vary with a huge pattern because the current is decreasing, but OCV is changing just very small. So a large variation in current, just only small variation in the voltage, because OCV depend on more on temperature and its photocurrent. So now the IV characteristics for the, like we have number of panels like new and old. Okay, so the sun resistance for new panel, it should be very high, because if the panel is very new, so the material is very effective, all the doping is very effective, there are no defects and all, so there will be very less recombination occur. Okay, and what will happen, the sun resistance will be very high and this contact resistance will be very low, because the panel is new. But so this curve will be for panel 1, or you can say new panel. But after certain number of years, the panel material will deteriorate and having some wear. Okay, so after that there will be some maybe defects also, some contact resistance also there. So this RS value will increase and this will be decrease. So if this resistance will decrease, then what will happen, some current will flow from this side. Okay, so then IL current will be decreased, because this pH is same. Initially no current was going from this resistance, but after certain number of years some current is also going from this resistance, and this is also increased, so less current will go through this RL circuit, or you can say IL. So the IL value will be decreased. Okay, so now let's have some questions. Just read the question. Is question number 1 is, both Fermi energy and band structure are flat when traversing across a semiconductor PN junction. So you have to tell that, is the Fermi energy band, Fermi energy or band structure are flat, or both, you can say the flat when we are traversing across a semiconductor PN junction. Is it true or false? Take 2 minutes and try to answer. It's true or false question. Anyone? Okay. So it will be false, because you can see we have covered in our slide that, yeah. So this Fermi energy level is, you can see, say flat. Okay, at the PN junction, but these are not flat. Okay, these are bending. Okay, so that statement is false, because only Fermi energy level is flat, but the conduction and the valence band levels are bending. So Fermi energy and band structure are flat when traversing across a semiconductor PN junction is false statement, because only Fermi energy is flat and the band structure is bending. So correct answer will be false. Question number 2. What are the advantages of an amorphous silicon over the single and polycrystalline samples? So basically, what is the, you can say the difference we have, like options like option A is it is more flexible to keep on a substrate or contour. It is possess more dangling bonds and thus the more number of defects. It is more effective in capturing solar radiation. It is less expensive. So what are the points which are correct? Maybe one or two, or maybe one or three, or more than one points can be correct. So take 2 minutes and try to answer. The question is, what are the advantage of an amorphous silicon over the single and polycrystalline samples?
It is less expensive.
Yeah, correct. Because what is the reason why the amorphous silicon is less expensive? Because if you want to make single crystal, then the methods that are involved to make the single crystal are very costly. Okay, the process is very delicate and require very decent and very delicate machines to make single crystalline samples, okay, as compared to the amorphous samples. So it is less expensive and it is also more flexible to keep on a substrate on contour. As we have in the earlier class, I have told that amorphous silicon, like we can cover the car roof or any roof structure on some PV panels, okay, using amorphous silicon because it is more flexible and it can be covered on any surface. So it is more flexible to keep on a substrate or contour. It is less expensive. So these are the correct answers. So option number 1 and option number 4. Okay. Now match the followings: new solar cell and edged solar cell. So there are two options: sun resistance RSH and series resistance, again sun resistance and series resistance. So what should be high or low? You have to match A and B with 1 or 2. So I have already told you in our previous slides what should be the values. Take 2 minutes and give the answer. Let's try to recall the basic diagram of the complete diagram in which RSH, RS and RL was there. Try to recall that. Try to recall IV curve also. Try to think about if your solar cell is very new, then what about the recombination losses I have told, because shunt resistor is depend on the recombination losses and series resistance is contact resistance. So if your cell is new, then your all components are new and they are working at their maximum efficiencies initially because the system is new. So based on that, can you answer? Okay. So if your cell is new, then it means that your material is completely new and working at their max efficiency. So the shunt resistor or you can say R subscript SH will be high or low. It should be
For
very
you,
high.
low. Acha, high.
High. Because if RS is a high, then it means that there will be no recombination current and no current flow through this resistance because it's very high. It will not allow the passage for current. Okay. So you will get maximum current to the load. What about the series? What about the series resistor? Series resistor, that is RS. It should be low or high. It is due to the contact, okay, contact resistance, okay, contact of, like you can say, terminal contact of like material of the semiconductor. So initially they are all working very fine. So it should be low. Okay. So if RS is low, it means that it will pass the maximum current to the load. So at the load you will get maximum current because we know the circuit now. This is your IPS current, then here your diode. Okay, so this is your RSH. This is RS and this is RF. So for new resistance, for new solar cell, this will be very high and this will be low. So maximum current will go to the load. After some years, if your solar cell is aged, then there will be some losses, there will be some defects also, there will be some wear also in the panel, okay, in the cell, okay, and there are various factors. So then what will happen? Some recombination current will also occur, some recombination will be occur, okay. The contact maybe are not working efficiently, they are having some issues. So this resistance will increase. So RS will increase and its RSH will be decrease. Okay. So now some current will also flow from here and this will resist more current. So less current will come into the RL. So the efficiency will decrease, you will get less current. So the correct answer is for new solar cell A1 high and resistor RS should be low. For aged solar cell, RSS should be low and series resistance should be high. Okay. So let's see the correct options: A1, B2, A1, B2, C3, A1, B2, and C2. Sorry, A1, B2, C2, D1. A1, B2, C2, D1. Yeah, this option is correct. A1, B2, C2, and D1. So option B is correct. Any doubt? Okay. Now what is the fill factor? So what is the fill factor? We have covered in our previous slides. What is the fill factor? Take 2 minutes and try to recall. For hint, you can consider the IV curve. In IV curve, we have discussed about the fill factor.
Sir, is it option 2?
Option 2, VMPP, IMPP upon VOC, ISC. Yeah, it can be correct. Yeah. So, is any other option also correct? Please check all options, because maybe it is not given that only one option is correct. Maybe more than one option can be correct. So, see all options. And meanwhile, I will explain.
Second and D?
Yeah, D can also correct, because this is just changing the configuration. Okay, changing the denominator. So option B and option D. Option B, VMPP IMP upon VOC ISC and VOC ISC upon VMPP are correct. Now we have seen that for I and V, so this is the short circuiting current ISC, and this is the OC, open circuit voltage. Okay, so for maximum, for ISC and VOC, this is the maximum point A. But in actual, we are at point B. So the values regarding the values of current and voltage corresponding to the point B will be VMPP and IMPP. So from our solar cell that is having this characteristics, IV characteristics, we can get this maximum value. Okay, the maximum power that can be drawn from the particular solar cell that is having this particular IV characteristics, that will be based on IMPP and VMPP. But theoretically, the maximum value can be this ISC and VOC. So this is the fill factor. Okay, so it is the ratio of the maximum and this VOC and ISC. So its value will be less than 1. So value near 1 can be considered as value as high, near 1 is considered as the best value. So whenever you choose solar panels, then choose based on the fill factor of that particular solar panel. Okay, so correct option is option B and option D. Option D is similar to B, just we have changed the denominator. We have just put denominator back into the, sorry, we have changed the numerator. Okay, so numerator just change, just at the bottom of the denominator. We can write it like this also. Okay, after rearranging, you can write VMPP IMP on numerator. Okay, so option B and D are correct. Now question number 5. Name the following symbols in the circuit. So you have given the circuit. You have to note the symbols. Okay, we have given like symbols A, B, C, and D, and the component like shunt resistor, load resistor, series resistor, photocurrent. So name the symbols. Okay, so take 2 minutes. Try to answer. For hint, we have just covered this in our last 2 or 3 slides. In recent questions, I have already mentioned all the
Sir,
names.
option first?
Option first, you mean to say that
A is
A.
the photocurrent, B will be the
Mhm.
shunt resistor, C will
Okay.
be resistance in series, and D is the load resistance.
Yeah. So your answer is correct. So we have already covered that A is IPH. IPH is photocurrent. So A will match with the photocurrent. This B is the shunt resistor, and it is due to the internal recombination of electron and hole pairs. So B will match with 1. The C is the series resistor, or you can say due to the contact resistance. Okay. So C, it's written as RS. It is B written as RSH, shunt resistor. Okay. So C will match with the third. Now the D is the load resistance. It is noted as RL. D will be load resistance. So A4, B1, C third, and D1. Okay. A4, B1, C third, and sorry, D will be D2. Okay, load resistance. Sorry, D is 2, load resistance. Yeah. So one catch is there. You can see here two accepted answer is there. So anyone want to know? Anyone want to tell that why this option is also correct? Option A is correct from our side, but in answer it is also given that A4, B1, C2 and D3 is also correct. Like C2 and D3. Option C is also correct. So what is the reason? Anyone? Again, I am giving you 2 minutes because it's very important to know, because more than one options are correct, and you should know that why though, when you have already matched option A and you will tick the option A, but option C is also correct. So what is that reason for that?
Sir, is it due to changing the bias, reverse bias?
No, that is no. It is not due to that reason. Just just think little bit more. It's very simple actually. The reason is quite very simple. Because you have given this diagram. Just consider this diagram. Okay. Now see this diagram, and based on this you have to name the A, B, and C. A, B, C, and D. Okay. Now these two options can be correct. You have given the correct answer initially, but option C is also correct. So what is the reason for that? Okay. So the reason for that is that because C and D are connected in series. Okay. C and D are connected in series. So they can interchange. Okay. Because we have given C or D. So either this can be load resistance or this can be series resistance. Okay. Or either this can be series or this can be load. Just don't confuse with the diagram that given in the don't confuse with the diagram that is given here. Okay, because they are in series, so they can interchange. This can be, this RL can be RS, or this can be RL, because there will be no effect on the circuit because they are in series. Okay, so the overall effect will be same. So this is very important point actually. So try to remember this whenever you are solving the assignment questions. So this type of tricky question will be there. Okay, so whenever you solve the assignment question, try to think in all aspects. Then only you will get the full marks. Otherwise, you will get the partial marks. Okay. Suppose if you only answer the option A and don't answer the option B, you will get only half marks. Because the registers C and D are in series, so we can say either of them can be the load or series resistor. Is it clear?
Yes, sir.
Yeah. Okay. So again, this is just the PN junction from our previous classes, just to recall some. Okay. This is the, like you can say again, bending is occurring. This Fermi level are in line. Okay, we have already covered this. Okay. The space charge region you can see. Question number 6. Open circuit voltage of a solar cell. The question is open circuit voltage of a solar cell. You have 4 options. First is varies with exponential of photocurrent, does not vary with temperature, varies linearly with temperature, or varies with logarithmic of photocurrent. So you have 4 options. I have already covered this, the expression for open circuit voltage. Okay, and I have also stressed on the points that on which the this open circuit voltage depends. Okay, so let's take 2 minutes and try to answer. Let me show you the expression of open circuit voltage that we have. Yeah, this is the expression. So just giving you the hint. The expression is, just look at the expression. VOC is equals to gamma KT upon Q logarithmic IPH upon I naught plus 1. So this is the expression for open circuit voltage. Again, VOC is gamma KT upon Q log bracket IPH upon I naught plus 1. See it, see this expression very carefully and try to answer the question. The question is, yeah, open circuit voltage of solar cell. Option A varies with exponential of photocurrent. B does not vary with temperature. C varies linearly with temperature. And D varies with logarithmic of photocurrent.
It varies linearly with temperature.
Okay. And is any other option is also correct?
Yes, I am confused between first and last, A and D.
Okay. So it's very simple actually. If the option is exponential of photocurrent now, so whenever you see the exponential variation, then there will be E. Okay. And whenever the logarithmic then there will be ln. So we have seen
D.
yeah. So in our VOC, we have seen that the expression is like ln IPH upon I naught. Okay. So it is the IPH in the bracket of ln. So okay. So there will be logarithmic variation. Okay. If you change the value of I, suppose I is 1 or I is 2, then the value will be log 1 or log 2. Okay, so the value will be in the logarithmic variation. Okay, so option D is correct, varies with the logarithmic of photocurrent, and T is in coming outside. Okay, so with linearly. So VOC is proportional to T and VOC proportional to ln IPH. Okay, so it's varying linearly with the T and logarithmic with the photocurrent. So correct options are option C and option D. Now let's come to the Shockley-Queisser limits. Okay, so these are the name of some scientists. They have given some limits of efficiency that can be obtained from a solar panel. So in unconcentrated AM 1.5 solar panel. Okay, so what is this AM? So this AM is air mass coefficient. Okay, so this air mass coefficient is optical path length. Suppose this is your Earth and this is your atmosphere. So as for this particular location, the solar radiation is incidenting in its own perpendicular in the straight direction. Okay, so this will be the minimum path. Okay, this is the minimum path. The optical path length related to the path length vertically upward. This is vertically upward path length. Okay, suppose the radiation in daytime, because this is maybe at the time of noon. But if you are in morning or evening, so maybe radiation is falling at this particular location in oblique direction. Okay, in this way. So the length from like A to B is minimum, and A dash and B dash will be more than this AB. Okay. So normally we consider this. Suppose if this is considered is like 1 times, then this length considered like 1.5 times. So we considered on average 1.5 times. Okay, so that's why this is 1.5. Okay, so AM 1.5 typically used for evaluating panels. So whenever we want to evaluate the panels, okay, what are the efficiency of the panels, then because every time the location is changing. Okay, the length may be changing, but on average we consider it's 1.5 times. Okay, so that's why we are considering this typically AM 1.5 typically used for evaluating the solar panels. So whenever like so for a particular unconcentrated solar panel, so the radiation are not concentrated on a particular point. So we are having unconcentrated solar panel, and it is AM 1.5 solar panel, so, and the radiation with a band gap of 1.34 electrovolt. So the band gap is 1.34 electrovolt. So what is the meaning of this 1.34 electrovolt? So any solar radiation that are having more than 1.34 electrovolt will take part in the electric current generation, and the radiation which are less than 1.34 electrovolt will pass through the solar panel. So based on this, we get the 33.4% efficiency, max efficiency. Okay. Suppose on a particular solar panel, if 1000 watt solar energy is coming, then from that particular solar panel you can get only 33.4%, or basically you can get only 334 watt of energy. Okay, so you can say 1/3 energy you can only get. So this is the efficiency for a solar panel which is having 1.34 electrovolt as a band gap. So this is considered a theoretical limit. Okay, suppose for silicon single crystalline 1.1 electrovolt we are having 32% efficiency. Okay, it is theoretical, but practically we get only 24%. As of now, 24% is accomplished, but theoretically we can get at 1.1 electrovolt 32% efficiency can be obtained. So the diagram of efficiency and the EG is like this. Okay, after a certain band gap, the efficiency again when you increase the band gap, when the EG value, the efficiency increases, and after certain it decreases. Okay, because if EG if the electrovolt is very high, then what will happen? This is your valence band and this is your conduction band. Okay, if you are getting more energy than required, then this electron will go to the very upper level of the conduction band, but the current space region is near to this lower valence, because at this lower end also there are some vacancies. Okay, so this electron will come to this lowest location. So it is having high energy, so it occupies this higher space, but below this already unoccupied spaces are there, so that will fill that particular space and release this energy in the form of heat. So that is of no use. Okay, so that's why after certain voltage it's again decreased, and at a particular voltage it is maximum. Okay, so why it decreases? So they are basically, so why we are getting only this 33.4% efficiency? So the reason is that we are having black body radiation, so it's about 7% losses. Okay, at room temperature. So because the solar panel at room temperature like radiate, because it is at some temperature. Okay, and actually it is around 75 degree temperature normally, so it radiates the heat due to its temperature. So 7% losses will be due to radiation, 10% will be due to recombination losses, because some electrons will go to the conduction band but again recombine with the hole in the valence band. So 10% will be due to the recombination loss and spectrum loss. So 90% will be unobserved, because suppose if you are having 1.1 electrovolt of band gap, then any radiation, because we know that radiation are having various band gaps. Okay, because we are having ultraviolet, we are having infrared, we are having visible spectrum. So the spectrum is having different wavelengths. So the wavelengths which are less than 1.1 electrovolt, band gap 1.1 electrovolt energy will not take part in the electricity generation from solar panel, so that they will be unobserved, or they will be passed through that particular panel. So we consider 19% is unobserved and 33% is having excess nu. Okay, excess nu means Eg is equals to H nu. So nu is very high, then electric potential is very high. So this will occur. So they will go to the very high conduction band and again release some energy and again come to the lowest band, the lowest band, and the released energy will be released in the form of heat. Okay, so that will not take part in the electricity generation. So that will also a loss. Total 52%. So majorly three losses are there: black body radiation, recombination, and spectrum loss. So black body counted for 7%, recombination 10%, and spectrum 52%. So if you total it and subtract from 100, then you will get around 33.4% efficiency limit. So this is the concept for this limit. Now, whenever we want to make the solar panel, then we have a positive terminal, this is P, and PN junction, this is a negative terminal. Okay, so solar radiation is impinging on the surface. So here you can see that negative terminal is in the form of fingers. So from this space, okay, you can see the space. From this space, the sunlight strike on the semiconductor, and at junction, the PN junction will do the work and generate the electricity. This is the positive terminal. So you can connect the load here. Okay, this is negative, this is positive. So after the solar radiance when strike on this, so the all we have studied from last 2-3 weeks, so all those will happen and you will get the current. Okay, so basically these are the efficiencies from different types of semiconductors. Like single crystalline can give up to 25% efficiency, polycrystalline 15%, and amorphous only 5%. So basically efficiency is decreasing, so the cost will be increasing, because amorphous can easily form as compared to polycrystalline and single crystalline. So the cost of this increases from amorphous to single crystalline, and the efficiency will decrease from single crystalline to amorphous. So this is example of amorphous silicon solar cell. Okay, here we have also a glass plate at top of it, then PN junction. Then we are having a transparent conducting oxide. Okay, transparent conducting oxide, and this particularly indium tin oxide is used as a transparent conducting oxide. At the bottom we are having reflective back content, so any radiation that is impinging on it again reflected. Okay, now we have do some anti-reflective coatings also. The formula for this is N1 equals to root N naught Ns. So N naught is the air, reflective index for air, and Ns is for glass. So glass it is 1.5, and for air it is 1. So the film coating will be root 1 into 1.5. It will come as 1.225. So this with reflective index coating we do in the amorphous. Okay. So as in this, you can see this negative terminal, okay, this positive terminal. So similarly, this reflective back contact will have some conductivity, and this transparent conducting oxide will also have conductivity. So this can be connected with the circuit. You can get the electric current. Okay. Now this is also very important, tandem cells. So as we have seen that the efficiency obtained from solar panel is very less. As you can see, it's like in the range of 33%, but in actual we are getting only 5%, 15%, 25% efficiency only. But using the tandem cells, we can get theoretical efficiency up to 80%. So how it is possible? Because if we are making a particular cell, then that cell is having some band gap voltage, and that is effective on this particular wavelength radiation only. Okay, but in tandem cells it can take multiple wavelengths, and every wavelength can take part in the electricity generation. Okay, so how it can happen? So so this is due to nanotechnology. Okay, so nanotechnology. So whenever we change the crystal, whenever we change the material structure on nanotechnology level, in nanometer level, then their easy value changes. Okay, so based on this, a single material can have different band gap electric voltage value. Okay, EV values, easy values. So we can make different layers. So suppose you are having a tandem cell that is having 4 layers. Okay, so this layer is having easy value of 1.5 electrovolt. This layer is having zero point 0.9 electrovolt. This is having zero point 0.5 electrovolt, and this is having zero point 0.1 electrovolt. So suppose if these are all connected in series. Okay, suppose these are all having layers one above other. Okay, suppose if your incident radiation, because we know that incident radiation are formed of various wavelengths. Okay, because it is part of UV rays, infrared rays, and visible rays. So different wavelengths are there. Suppose if particular ray, there are 4 rays. Okay, so ray 1 is having 1.8 electrovolt, so it will strike on this and it will give the energy to photon. Okay, and it will take part in the electricity generation. This second is having voltage of 1.0 eV. So this layer is only this layer is having 1.5 electrovolt. So 1.0 electrovolt radiation will pass through this layer and strike to this layer, and this layer is having 0.9 electrovolt. So now this layer will take part in the generation of photo current. Okay, because the voltage 1.0 is more than 0.9, and now the radiation number 3, it is having voltage of 0.7. So again 0.7 is less than 0.9, so it will pass through both this layer and this layer and strike to layer number 3. Okay, at layer number 3, the band gap value is 0.5 electrovolt. So again here the value, the radiation is 0.7 electrovolt, more than 0.5 electrovolt. So again we will get photocurrent. Now this layer, sorry, now this this radiation is having voltage of 0.3 electrovolt. So this will pass through layer 1, layer 2, layer 3 and strike on layer 4 and generate photocurrent, because layer 4 electrovolt is 0.1 only, which is less than 0.3. So in this way you can see we can get the photocurrent from around various wavelengths. Okay, from various electrovolts. Okay, so from high band gap cell to low band gap cell we can generate from a single cell. Okay, by making the different layers, and based on this we can get the maximum of solar radiation and we can convert that to electric current. So with several tandem cells and concentrated sunlight, theoretically more than 80% efficiency is possible. Okay, so research is going on this, but the cost will be very high for this. Okay, because you have to make different layers, PN junctions. Okay, and every layer is having different band gap value. Like visible spectrum length is around 400 nanometer to 700 nanometer, violet to red, and the corresponding band gaps are 3.1 electrovolt to 1.8 electrovolt. Now this PBS, a direct band gap semiconductor. So the bulk of PBS, the band gap of bulk PBS is around 0.4 electrovolt, but when we are applying nanotechnology, so the band gap of nanocrystalline PBS can be varied to 4.0 volt. So you can see the bulk PBS was having only 0.41 electrovolt, but we can, by changing its crystalline structure on nano level, we can change the band gap value up to 4.0 electrovolt, which is very huge. So in this way, we can make multiple layers and we can make tandem cells that can give you the high efficiency. So question number 7. So bulk lead sulfide material. So lead sulfide is PBS. So bulk lead sulfide material can absorb the full visible spectrum because you have four options. It is a direct bandgap semiconductor. It is an indirect bandgap semiconductor. Bulk lead sulfide bandgap lies in middle of this region with respect to wavelength. Bulk lead sulfide bandgap correspond to a longer wavelength than that corresponding to this region. So what is the answer? Think about it. Let's take 2 minutes. Okay. So the correct answer is option 4 because the bulk lead sulfide band gap corresponds to a longer wavelength than the corresponding to this region. So the region given is was visible spectrum region and the corresponding wavelength as compared to bulk lead sulfide is to a longer wavelength than the corresponding to this region. So correct option is D. Question number 8. Space solar cell improves solar cell efficiency by using materials with space band gap values. So in previous 2 or 3 slides I have explained this. So take 2 minutes and try to answer. We have to increase the efficiency. So and for your hint I can give that from this cell we can get up to more than 80% efficiency. We have just discussed it like 5 minutes back only. What is the correct answer? Anyone? Take 2 minutes and answer.
Sir, is it option D?
Option D. Okay, so tandem solar cell improves solar cell efficiency by using materials with same band gap values. Suppose if you are having same band gap values, then what will happen? Then that particular uh, material is only effective in particular like band gap values only. Okay, because you are having same band gap values, but we are having infrared, UV spectrum, infrared spectrum, visible spectrum. So every spectrum is having different EZ values. Okay. So it should be same band gap value, different band gap values. Just think about it. Because I have explained in our previous in this. Okay. So what was here? We were having 1, 2, 3, or 4 solar radiations, and we were having some layers, and every layer is having a particular band gap value. Okay, like layer 1 was having 1.5, layer 2 was zero point 0.9, layer 3 was zero point 0.5, and layer 4 was 0.1 electrovolt. So high band gap cell to low band gap cell. You can say this was 1.5, this was zero point 0.1, and in between there were some 0.9 and 0.5. So we are having multiple band gap values. Okay, so whenever different radiations are striking, so suppose if one radiation is passing through this value, but again we are having a cell here, and that cell has a value corresponding to this wavelength, so it will generate photocurrent. Okay, so now just think about the answer. Again, take 1 minute and think about the answer now.
Sir, option B, tandem solar cells with different band gap values.
Yeah. So the correct option will be option B. Tandem solar cells with improved solar cell efficiency by using materials with different band gap values. Because if we are using different band gap values, it means that we can capture the maximum of solar radiation, because solar radiation is composed of different band gap values. Okay, so we are making tandem cells by same materials layers, but with some help of nanocrystalline technology. Okay, we are changing the band gap values of same material using nanotechnology like PBS. The band gap value can increase up to 4.0 electrovolt from 0.4 electrovolt. Okay, so by using nanotechnology, we can change the value of a particular material, and that material's layer which have different band gap values can make the tandem solar cell, and that thermal efficiency goes up to 80% for particular configuration. Okay, so we can get the more efficiency using tandem solar cells, but the cost is very high as of now. Maybe in the future it will practically available, and the cost will also considerable. If the refractive index of a glass and air is 1.5 and 1 respectively, then what should be the ideal refractive index for anti-reflective coating material? So we have discussed it. Like if you have to know the refractive anti-reflective coating material N, then you should N0 and Ng. Okay, so this is the formula. This is for air, this is for glass, this is for coating for the anti-reflective coating material. Okay, refractive index for anti-reflective material. So what will be the answer? Let's find out.
1.225.
Okay, so when we solve this, we get 1.5 into 1 to square root of 1.5. It will be 1.225. So the correct option will be option C. So question number 10, according to Socle coincident limit of the simple PN junction in a 1.5 solar radiation with a band gap of 1.3 electrovolt. So answer is already given here. Okay, so as we have already discussed it, so these scientists have experimented and find out that for unconcentrated solar for single PN junction, okay, and for one AM 1.5 solar radiation with a band gap of 1.34 electrovolt, okay, they obtained poor efficiency. Okay, so the answer will be unconcentrated and 33.4. So correct option will be option A. It is a direct statement, or we have already covered it in this slide. Okay, in this slide we have covered it. And what are the losses? That were black body radiation, recombination losses, and spectrum losses. Due to these losses, we are getting only 33.4% of efficiency only. Now let's have this simple true false questions. Question number 1 is the Sokle Quasar limit suggests that a single junction solar cell has an efficiency that can reach 100% when the sun is overhead. Is it true or false? Take 1 minute and try to answer.
False.
Okay, it is false because we have already covered that the efficiency can up to only 33.4%. Okay, and what is the reason? Because there are number of losses. Okay, so the question number 2 is the maximum power point of a solar cell occurs at open circuit voltage. True or false? Means the maximum power point, the point where you can get the maximum power. Is it at OCB? Try to recall.
It is at the fill factor, I think.
Yeah, no, fill factor is just a representation. It is asking the maximum power point. Where is it occurring? Where is it occurring? Okay, this is ISC and this is VOC. At which point it is saying that maximum power point of solar cell occurs at open circuit voltage, at this voltage. So is it occurring at this voltage or some other voltage?
Lower than the VOC.
Yeah, lower than the VOC, maybe some here. Okay, at this voltage maybe it is occurring. So it is also false because the maximum power point cannot be, because if you are at open circuit voltage means your circuit is not complete, circuit is open. Okay, so current is 0, so power is 0 because the current at open circuit is 0. Question number 3, the maximum power point of solar cell may vary from manufacturer to manufacturer. The maximum power point of a solar cell may vary from manufacturer to manufacturer. Is it correct? It is true or false?
True.
Yeah, because it depend on the defects, it depend on the recombination losses, it depend on the material structure. Okay, it depend on number of factors. If you are having same materials, but it depend on the complete configuration. Okay, so maybe the different manufacturer have different systems, machines to configure the PN junctions. Okay, so it can vary. Okay, so it is true. During reverse bias, the N side of PN junction alone is affected by the applied potential. During reverse bias, the N side of PN junction alone means only the N side is affected or both sides are affected when we are running in reverse bias. Both are affected because at the both side, on the side of P there will be more electrons, and in reverse bias the p side is also connected with the negative terminal, so more electron will try to go, and the same side in the p, more holes will be there, and that side is also connected with the positive terminal, so the hole will also try to go there, but they are having some resistance. Okay, so both sides are affected. Charge density as a function of position is constant across a p-n junction. True or false? Charge density as a function of position is constant across p-n junction. So what is the charge density as a function of position? So we have already discussed in the diagrams. So charge density is a function of location. So that will be dE upon dx. This is charge density. Okay. It's function of location. Yeah, this is charge density. Okay. Rho. And this is the voltage. Band voltage with the location. So this is the charge density. So it is constant or varying.
It's constant.
Charge density is a function of position is
Is a
constant.
function of position. It's a truth statement, I think.
No, it's false. Because when we are talking about p-n junction, okay, so for p-n junction, it's changing from negative to positive. Okay, so charge density is a function of position is constant across p-n junction. It is not. Okay, it is false. It is varying. And for this, during reverse bias, the n side of p-n junction alone is affected by the applied voltage. It is false because both sides are affected. The maximum power point of solar cell may vary from manufacturer. Yeah, it's true because they are having different losses. Now, the maximum power point of solar cell occurs at open circuit voltage. It is again false. This is also false. So what are the conclusion? Okay, so these are the conclusion from this week. We have conclusion that the p-n junction stabilize the electron hole pair. So basically the p-n junction stabilize the electron hole pair, okay, and generate the current. The p-n junction solar cell is a current source and has to used accordingly. So basically the p-n junction is a current source. Okay, it is not a voltage source. Voltage is there, but the measure it is source of a current. Okay, it is considered as current source. Okay, and the p-n junction stabilizes the electron hole pair. The solar cell is a current source. Okay, the IV relationship is very complicated. Okay, it is not like constant for every material or every p-n junction. It is very complicated. It depends on the various factors. Okay, we have seen the equation now. It's a equation. It's depend on the resistance. Okay, various type of resistance are there. IV resistance is very complicated. Open circuit voltage is not the most important parameter. It's very important. OCV is not the most important parameter. The fill factor is the most important parameter because OCV can be same for different cells. Okay, but the fill factor can be changed. But the fill factor decide the maximum power from the cell. So fill factor of a solar cell is important. Solar cell must be coupled with an end use that utilize the MPP. Okay, so it should be coupled with an end use, or maybe it should be applied with the load that can utilize with the maximum power potential. Parts of a solar cell are designed to increase the efficiency of solar cell. Yes, we should design the parts so it will have minimum defects, minimum resistance, so we can get maximum efficiency. Shockley-Queisser limits indicates the limitation of a single junction solar cell. So single junction solar cell can go up to only 33.4%. It is having some limits. Tandem solar cell can overcome these limitation. So if we go for tandem solar cell, it's for single junction only. Okay, If you are having multiple junction, we are having multiple layers, so we are having tandem solar cell, so we can overcome this limitation and can go up to 80% of efficiency. Okay, so I think these are for today's class. Time is also almost completed. So thank you for attending this session. This session was live session 6 for week 6 content. Today we have discussed, we have revised the week 6 content and we have solved sample questions. Okay, or maybe these questions will be very helpful to you in your assignments, and maybe you will be able to solve this question, your assignment question, and maybe your concept is more yeah, like clear now. Or further, if you want to further this discussion, you can refer the professor's class notes also. And I will share, and the NPTEL team will share the course content with you. This PPT and this video, this recording will be shared to you. So you can refer those who were not able to attend today's class can see this recording and also can access this PPT. Okay, then I am stopped presenting. Okay. Okay, thank you very much. Thank you very much for attending this session. Thank you everyone. I'm ending the meeting. Thank you.